All right. Hey, AGU, Adam Ward here. I want to talk to you about an idea called the channel source hypothesis. This is work from myself and Steve Wanzel, the U.S. Forest Service. And what we'll be presenting today is empirical evidence for in-channel solute dynamics in response to storm events, or concentration discharge and what causes it, to put it plainly. So we'll take you today to the H.J. Andrews Experimental Forest. In particular, we'll take you to Watershed 1, which is second order basin near the outlet of the LTER. Watershed 1 is a long studied basin. There is a extensive well network that's been in place for about 20 years. This has been the site of much work on riparian and hyporheic hydrology. And key observations that we'll look at today include in-channel discharge measured at the weir in the basin, and then stream chemistry sampled in the stream, a network of wells in the hyporheic zone and riparian zone, subsurface water collected in the hill slope, and also subsurface samples collected in a saprolite fracture. Now, what we're going to do is zoom in on one storm event response that we monitored all of these different water sources before, during, and after. And for simplicity's sake today, we're just going to look at DOC, although we did sample these for a host of different solutes. The important thing for you to notice here is that prior to the storm event, we had relatively uniform DOC across all of the places that we were studying. When the storm event hits, we get a rapid in-channel response. So the stream hydrograph rises. That's the gray in the background of the lower panel. And stream DOC exceeds all DOC measured in all other locations, excepting one measurement in one well. In other words, the stream is more enriched in DOC than any other source that's present. And then that concentration slowly fades back away to its slowly and eventually in time to its pre-storm concentrations. So what we have here is a classic clockwise hysteresis pattern where early in the hydrological response, we get a disproportionately high concentration. So in other words, to explain this, we need a rapid source of water that is also mobilizing a significant amount of DOC. So what we're going to do is walk through a host of conceptual models and ask, okay, right, we've seen plenty of CQ relationships. What can explain these observed dynamics in our system? So the first of 6 classes of models is Hortonian or infiltration excess overland flow. For each of our models, we'll have an idealized schematic of the watershed on the left-hand side, where DOC is represented by the orange dots. Red representing the key flow paths or the hydrological components of the conceptual model. And then the table is going to summarize what would it take for this conceptual model to work. So for Hortonian overland flow, hydrologically, you would need to generate infiltration excess overland flow. In other words, we'd need to have precip that couldn't be infiltrated into the subsurface. In our case, you can see in italics there, the evidence is that this flow generation mechanism has never been observed nor reported at our study site. In the right-hand panel of the table, DOC requirements, you would, in order for this to explain what we observed, you would need DOC sources to exist near the land surface and be mobilized by that runoff. Well, we didn't measure that directly because there is no hydrological basis. We conclude that this is not a meaningful conceptual model for our study site. Similarly, we can look at saturation excess or Dunnian overland flow. Hydrologically, we get this when lateral or longitudinal expansion occurs from the channel network. Schiff et al. 97 extended this to be lateral or to be longitudinal along the channel. In order for this to work hydrologically, we would need to witness an expansion of the saturated zone, either laterally or longitudinally, neither which we observed. And in terms of DOC, we would need a source of DOC that was higher than the stream water pre-event and rose to intersect the surface. We have neither. There is no pre-event DOC that is sufficiently enriched to explain this. Thirdly, we come to a group of conceptual models, all of which involve translatory flow from the hill slope to the stream. So these invoke different mechanisms, but in all cases, the idea is that high DOC water is stored in or beneath the hill slope. And when it rains, that water is rapidly mobilized to the stream channel. Now, in our study site, past work by myself and Steve Wanzel and several others have confirmed that travel laterally from the hill slope to the stream is on the order of 20 or more hours. And we saw a storm event response and DOC enrichment within less than 2 hours. So hydrologically, we don't have a way to get water or DOC quickly enough to the stream. Moreover, we don't see high DOC in the hill slopes that could make this mechanism work. So on that basis, we conclude that transitory flow from the hill slope is not the likely mechanism. Still others have suggested translatory flow, but sourced from the O horizon. This requires high DOC to be mobilized from those organic rich soils on the hill slope and somehow rapidly bypass the riparian zone. Again, timescales across the riparian zone, a lack of transport mechanism linking the hill slope to the stream mean this is hydrologically infeasible. And again, we did not see DOC in our hill slope wells or our near hill slope wells that would be sufficient to explain this. What about translatory flow sourced from tree canopies? This is a mechanism that's been reported in the nearby watershed 10 at the H.J. Andrews. And so while this was reported nearby, again, the transport timescales across the riparian zone are simply preventative. We can't get water and DOC from the hill slope to the stream quickly enough to make this a meaningful mechanism in our study site. Preferential fracture flow. This is possible. We know that the basin is underlined by a fractured igneous and metamorphic bedrock. We know that there's a fracture network through the saprolite and that we could potentially bypass flow. We do expect that hydrologically this mechanism is possible. However, the wells that we have in the saprolite never reached a DOC that would be sufficient to enrich the stream. In other words, while the mechanism may exist hydrologically, it doesn't exist as a source of DOC. Now, we also note that base cations, which I'm not showing in this presentation, didn't change in the stream, and that would have been expected as further evidence of a significant sourcing of water and solutes from the fracture flow. So taken together, we still don't think that this is the right mechanism. What about translatory flow displacing riparian water? So you've got high DOC water in the riparian zone, and when it rains, that new rainfall pushes older DOC into the stream channel. This is a conceptual model first published by McGlynn and McDonnell in 2003. And I'll note that this has been reported for our site. This reporting from Aaron Hood and others was in our study basin and was reported based only on the observation of that clockwise hysteresis at the outlet. So with only outlet measurements, this mechanism was invoked to explain them. However, when we went back and actually tried to validate this, which was our initial motivation for the study, we found something quite different. Hydrologically, the storm event doesn't change the flow paths through the riparian zone. There's no pressure wave. There's no mechanism to mobilize that water any faster than it would have been. That's work from Tom Volz and others. And similarly, you would have to have high DOC sources in the riparian zone. And again, the stream is higher in DOC than anywhere else that we measured in the catchment. In other words, we lack a hydrological basis and we lack a source of DOC. Fifth potential model is that it is the O horizon from the riparian zone itself. So rather than being sourced from a hill slope, this is the O horizon in the valley bottom already. This would require lateral preferential flow that bypasses the colluvium in the valley bottom and would be perched, if you will, in the O horizon. We have no hydrological mechanism that would cause this to happen. The timescales are essentially longer again than we think. And yet again, we don't have a high source of DOC. So while this mechanism has been reported, it's not likely the mechanism at our site. Finally, a group of models identify spatially discrete patches that can be rapidly connected to the stream channel, potentially bypassing porous media where a distal DOC source could be rapidly connected. For example, Gannon et al. In 2015, not 2915, invoke this mechanism to explain sourcing of DOC from distal patches that causes rapid responses in the stream channel. And so, in our site, we don't have much in the way of bedrock outcrops, and we don't have a mechanism that could connect those distal patches to the stream channel. In short, that wide colluvium-filled riparian zone simply takes too long for flow to cross to have any distal sourcing. Okay, so we've just run through nearly 100 years of conceptual models that link runoff generation and DOC to in-channel discharge concentration relationships. In other words, we have falsified a host of existing hypotheses or conceptual models. With none of those sufficiently explaining our observations, we set forth to pose a new hypothesis. What could be happening at our site? And the explanation we pose, Steve Wanzel and I call this the channel source hypothesis. In other words, we believe that the DOC that we are seeing in the stream channel was in the stream channel to begin with. In contrast to all of the conceptual models I've presented up until this point, what that requires is us to functionally decouple sources of water from sources of DOC. How would this work? When the stream channel responds, with water being sourced via whatever mechanism generates the stream pulse, the channel stage goes up, we increase energy and turbulence in the channel. The stream channel contains deposits of channel leaf litter. We know that there's a seasonality to DOC. At this time of year, one of the first major rain events after the summer, which is dry in this Mediterranean climate, we expect that DOC will have formed in leaf packs in the channel. So when we get a turbulent pulse of water, we flush that DOC. In other words, the DOC source and the water source do not have to be in lockstep. We're not the first folks to think about this in terms of DOC. There are a few papers from Meyer, as well as one from Buffum about 20 years ago that report or suspect mechanisms of this sort. Now, we're not not only are we not the first to think about this for DOC, but this is not a model that is unheard of. The image on the left is meant to represent sediment transport, where the stream is broadly recognized as a persistent and meaningful source of fine and coarse particulate matter that can be transported and mobilized in response to storms. River continuum concept on the right-hand side, emphasizing the idea that DOC can be generated and processed within the river corridor itself. We don't need hill slopes to source DOC in all cases. So if other disciplines have dealt with in-channel sources, why haven't hydrologists? We believe that hydrologists have overlooked this as a source because the stream doesn't generate a significant amount of runoff. I'm showing you here my favorite hydrological cycle. This is from Horton 90 years ago. And circled in dashed red is Horton's conceptualization of where precipitation meets the land surface. It's primarily on the ground surface. He's got interception. He's got evaporation of precip while it falls. There is no mechanism for rain on small streams. It's simply a small flux of water. So we as hydrologists are tending to be interested in forecasting water and using DOC or other solutes as a basis to make those hydrological insights. Because the channel itself is not a major source of runoff, we suspect that hydrologists have then assumed that it was not going to be a major source of mass loading. So we haven't taken the time to consider what might happen if our sources of water and our sources of solute mass could be decoupled from one another. So on this basis, Steve Wanzell and I pose to you that the channel source hypothesis is worthy of consideration as one of a potential suite of hypotheses that might explain observed concentration discharge relationships. Key points to take home. After reviewing approximately 100 years of literature, we've uncovered a host of conflicting conceptual models. Stream ecologists, for example, geomorphologists, have no problem embracing the stream as a source. It's simply that our discipline, hydrologists, hasn't been considering stream sources. And we believe that's primarily because, again, the stream is not a major source of runoff. Secondly, our disciplinary perspectives shape the way we think about DOC sources. For a stream ecologist, DOC might be the object of a study. For a hydrologist, it's an indicator of something else happening. And so it's really these disciplinary differences that have caused this bifurcation of conceptual models, where for hydrologists, the stream is simply an exit for water to leave the landscape. It's an integrator of sources. But for stream ecologists or geomorphologists, it may be a predominant source in their conceptual models. Finally, we hope, one, that this has given you some appreciation of the varied conceptual models that exist to explain why hysteresis could occur. We believe that the channel source is at least a hypothesis that should be considered alongside other mechanisms. And perhaps most importantly of all, CQ relationships at a basin outlet do not directly indicate internal mechanisms. Simply the evidence that hysteresis exists is not sufficient for you to make a judgment about where that water and solute was sourced from. If you're not measuring internally in the catchment, we've presented to you today now 7 unique mechanisms by which that the same hysteresis pattern, in our case clockwise, could be generated. So our strongest encouragement when you're interested in CQ relationships and you want to try and explain them, it would be helpful to work through this list of mechanisms and ask yourself, which of these can I falsify? It may be the case that you have more than one that you're unable to falsify, which is good science, right? The inability to falsify a hypothesis means it is plausible. And that's a great motivation or a great basis to continue your study and actually go collect the right data sets. In our case, to pick on our own faults, we didn't set out to prove the channel source hypothesis. We backed into it because nothing else fit. And so that's now motivation for us to go out and actually validate this and see if we can't tie this DOC pulse back to its sources in channel leaf packs. All right, thanks for your time, everybody. I hope you found this helpful, and I would love to chat with you via email or Zoom or whatever the right mechanism may be. Thanks, everyone.